Okay, so in this video, we want to begin to now combine together situations that involve both linear and geometric growth and decay. And this is going to enable us to deal with more realistic loan and investment situations where you would borrow money, but you would then make repayments. So the loan, for example, is earning compound interest, which is the geometric growth, but you are also paying money back on a regular basis. You're making a regular repayment every month, which is going to be some linear decay. So we want to be able to combine various things. So if you might have an investment, you might invest a large sum of money into an account, it earns compound interest, and you also continue to add money to that account every month. Okay, so we want to be able to deal with those two different things, both the interest being earned, which is the geometric growth, and also linear decay or growth, depending on whether we're adding payments in or making repayments. So we're going to, this second half of the topic of the Recursion and Financial Modelling unit is really around dealing with all those situations. And we're going to look at different ways to work with those situations. So the first way is to continue what we did in the previous videos, which is to use a recurrence relation. Now, the key difference here is when we have both geometric and linear growth, we can't then convert our recurrence relation into a rule that enables us to find the nth term. So the recurrence relation really is limited to only being able to use the recurrence. So by that I mean you can't just straight away work out how much will be in the account in 20 years' time. You would have to do 20 years worth of recurrences to get to that point. And there is no way around that. You cannot create a formula, okay? Or certainly not in further maths. We're going to then look at, after this video, some other ways that we can deal with these loans, because obviously constantly having to use the recurrence relation is going to be pretty cumbersome. So in the next video we're going to look at an amortization table, which is also a bit limited, but obviously if you're adept at a spreadsheet, it can be an efficient way, but it's a little limited. After that we will introduce the finance solver application in your CAS, which is going to enable us to deal much more flexibly with all sorts of different loan situations. That isn't to say that you don't need to know how to do the recurrence relation though. Okay, so a recurrence relation might also combine linear and geometric sequences. In these cases, the recurrence relation would be of this form. Now we're missing an important bit. We're missing V0, okay, which is an important part. So we would get V0, the initial term in the sequence, and then each term in the sequence, Vn plus 1, would be obtained by taking the previous term, Vn, multiplying it by some value, and also adding or subtracting some value, okay? So let's write down the first 5 terms in each of the following recurrence relations, which combine both geometric and linear growth and decay. Right, so if P0 is 12, we get Pn plus 1 by multiplying the previous term by 0.5 and then adding 8. So P0 is 12, so first term is 12. Then if we multiply 12 by 0.5, we get 6, and add 8 to that, we get 14. Multiplying 14 by 0.5, we get 7. Adding 8 onto 7, we get 15. Multiplying by 0.5, we get 7.5. Adding on 8, we get 15.5. Halving 15.5, we get 7 3/4, 7.75. Adding on 8 would give us 15.75. Okay, so there's the first 5 terms. You can also get your CAS to recur it. So 12, press enter to confirm that, and then multiply by 0.5, add 8. Next term is 14, 15, 15.5, 15.75. Okay, second sequence in part B, Q0 is 5, Qn plus 1 is 3 times Qn minus 20. So we take the previous term, we multiply it by 3, and then we subtract 20. So if we start with 5, we multiply 5 by 3, which is 15, and we subtract 20 is negative 5. Multiply negative 5 by 15, which is negative 5 by 3, which is negative 15, and subtract 20 gives us negative 35. Multiplying negative 35 by 3, getting big now, negative 105, and subtract 20, negative 125. Multiplying negative 125 by 3 is, what's that going to be, negative 375, subtract 20, negative 395. Alright, let's just check my mental maths. I'm not going to claim to be outstanding at mental arithmetic. Alright, so I've confirmed 5 as my first value. I'm then going to multiply that by 3 and subtract 20. negative 5, negative 35, negative 125, negative 395. Phew. Alright, third sequence, R0 is 3. Rn plus 1 is found by taking Rn, the previous term, multiplying by 4, and then subtracting 9. Okay, so our first term is 3. Our next term is 3 times 4, which is 12, and we take away 9. That's also 3. 3 times 4 is 12, we take away 9, that's still 3. 3 times 4 is 12, we take away 9, that's still 3. And we can see that in this sequence we're actually going to get the same term every time. And that's going to become a bit important later on when we talk about particular types of loans and investments. So let's just confirm that again. So 3 was our first term, and then we multiply by 4 and subtract 9. We get 3 again, 3 again, 3 again, 3 again. So we're seeing 3 different types of sequences here actually. We're seeing a sequence that converges, the top one. We can see that those numbers, they're still getting bigger, but they're getting bigger by a smaller and smaller amount. So they're going to actually converge to a point, okay? They're certainly not going to, it's getting bigger by a smaller and smaller amount, so it's approaching a sort of limiting value, potentially. The second sequence is not converging at all. It's getting, well, not bigger and bigger, it's getting more and more negative. But that would only continue to happen. The third sequence is remaining constant, okay? And that's because when we do 4 times 3, that essentially increases by 9, and so then when we subtract 9, we get back to our starting value again. Now, obviously, if I just changed, it's all about everything there working together. If I were to just change, if I were to change the starting value to be 2, all of a sudden when I double 2 and subtract 9, I don't get back to 2. Sorry, when I multiply 2 by 4 and then subtract 9 from that, I don't get back to 2, and so just different things would happen. Okay, similarly, if I were to make this 4 times 4 is 16, subtracting 9 from that is 7, so I don't get back to 4, it's going to continue to grow, okay? So different things will happen, and as I said, we'll look at a specific financial maths application where that's important down the track. Okay, so, and that's what that little paragraph talks about. Right, let's have a look at an example setting up the recurrence relation ourselves. A large lake is home to a population of flathead fish. Due to healthy conditions in the lake, the population of flathead is growing at a rate of 20% every month. Fishing licenses currently allow 2,500 flathead to be taken from the lake each month. There is currently 10,000 flathead in the lake. Set up a recurrence relation to describe the size of the population of flathead, Pn, after n months. Okay, so we need to use P. So this is an important exam technique. Make sure that you use the letter consistent with the question. Okay, so it's going to be P0, Pn plus 1, Pn, etc. So P0, currently 10,000 flathead fish. The population is currently, the initial population is 10,000. Okay, then to get Pn plus 1, we increase it by 20%. Okay, so we're going to do 1.2 times Pn. But then 2,500 flathead fish are also removed from the lake because of fishing. Okay, so every month we also take away, we increase the population by 20%, that's just the growth, they're breeding, and then we fish out 2,500. Okay, so that's what's going to happen from month to month. An increase of 20% and then subtracting 2,500. And we start from 10,000. So find the size of the population of flathead after 1, 2, and 3 months. So we're going to work out P1, P2, and P3. Okay, let's get the recurrence relation happening. So 10,000 is our starting value. We're going to multiply by 1.2 and then subtract 2,500. Oops, 2,500. Okay, so we get 9,500 fish at the end of 1 month. Repeat that again. 8,900 at the end of 2 months. And repeat that again. 8,180 at the end of 3 months. Is the population increasing or decreasing? It's clearly decreasing. So what that means is the 20% increase each month isn't enough to counteract the fact that we're taking out 2,500 fish. So we're fishing more than the population is growing. So it's not a sustainable rate to allow people to fish out of the lake. If the fishing regulations are not changed, how many months will it take for flathead to become extinct in this lake? Okay, so we're going to keep recurring until we've got no flathead. So we're up to 3 months. 4, 5, 6, 7, 8. Okay, so it's going to take 9 months. They won't be extinct after 8 months, so it will take 9 months. So P9 is negative 399. So therefore, it will take 9 months. Now technically it would take somewhere between 8 and 9 months, but with the recurrence relation we can't be more precise than that. The answer is not 8. It's not extinct at that point. After 9 months there will definitely be no more flathead left. A similar question that you might get with something like this would be, okay, well then what do we need to change the fishing license to so that the population doesn't decrease? And that's about thinking about the 20% increase. So the reason that's decreasing is because when we increase by 20% of 10,000 is 2,000 fish. So we're only adding in 2,000, yet we're taking out 2,500, okay? And so that means we get less fish after 1 month. And then the 20% increase will be even less than 2,000 fish, and we're still taking out 2,500. So it's going to increase by even more, okay? So what you want to kind of think about is that balancing. So if the 20% increase means that the population is naturally increasing by 2,000 fish in the first month, then if we were to fish out 2,000 instead, we would still have 10,000 fish, and we would keep the population steady at 10,000. If we were to fish out less than 2,000, the population would start to grow because they'd be breeding more than we're fishing out. Okay, so let's have a look at an application in the context of reducing balance loan. So sequences which combine linear and geometric growth or decay are far more realistic when it comes to financial applications. So as I've said, when someone takes a loan, they don't wait till the end of the loan period to pay off the loan in full after it's earned all that interest. Instead, we make regular repayments throughout the period of the loan so that the final balance of the loan eventually decreases to zero. And we call this a reducing balance loan. And we reduce the balance to zero by making sure that the repayment every month is more than the interest we earn every month. Okay. So for example, consider a $2,000 loan paying 8.4% per annum compounded monthly. The borrower makes monthly repayments of $174.35 until the loan is paid off. Okay, so first we work out the monthly interest rate is 0.7%, hence each month we'll be increasing the balance of the loan by 0.7%, which means multiplying by 1.007, and then decreasing the balance by $174.35, so subtracting $174.35. So therefore we've got that combination of the linear growth from the interest and, geometric growth from the interest and linear decay from the repayments. Okay, so we can sort of plot out what would happen. So if we start with 2,000, after 1 month we add on our 7% interest, which gets us to $2,014, but then we subtract our $174.35, and so that's the balance after 1 month. That then becomes the beginning balance for the next month. We increase that by 1.07, and then we subtract our repayment of $174.35. That then becomes the balance for the start of the next month. Increase by 0.7%, subtract our payment, okay? And we can keep going forever until we see that here, after 12 months, the balance of the loan would have been reduced to zero. Technically, it becomes negative if we were to follow the same pattern. So in practice, we would actually adjust the final payment. So instead of making a final payment of $174.35, because that would mean we overpay the loan, the last payment would just be, so the final payment would be adjusted, and instead of paying off $174.35, we'd pay off $174.31 so that gets to exactly zero. Okay. So that's what that paragraph is talking about there. So we can work out the total amount that we've paid over the course of the loan. Okay. So we've made, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 payments. 11 times $174.35, and then the last payment was one payment of $174.31. Okay, and so we add all that up and we work out that over the course of the 12 months, in total we made payments of $2,092.16, which means that we can work out the interest that we paid. We borrowed $2,000, so the total interest we paid over the course of the loan was $92.16. And if we work that out as a percentage, it's nowhere near 8.4% per annum, and that's because it's only 4.61% per annum, and that's because we're reducing the balance every month. So it's a percentage of a smaller and smaller amount, and so over the course of the loan you don't end up paying 8.4% of $2,000 because the balance of the account is only $2,000 right at the very start. Every moment after that it's less than that. Okay. Alright, so that's talking about why is the overall percentage of interest paid less than 8.4%, and that's because the balance is reducing each month. And so interest is being calculated on a smaller and smaller balance. So we're actually, apart from the first month, never actually calculating 8.4% of $2,000. Okay, the recurrence relation that would describe this loan. So the initial balance was 2,000, sorry. So to get the value of the loan after n plus 1 months, we take the value of the loan after n months and we multiply it by 1.007, which was our monthly interest rate, and then we subtracted $174.35. So there's the recurrence relation to describe that particular loan. Alright, so generally speaking, we could have our recurrence relation here. Our R value is going to be to do with our compound interest rate, okay, so and the compounding period. So lowercase r is the interest rate per compounding repayment period, so we had to work that out as 7.7% per month in the previous example. And then to work out the multiplying factor, we do the 1 plus r over 100, and then D is going to be our repayment value, okay. Alright, so Jennifer borrows $2,000 to purchase a new computer. Her loan pays interest at a rate of 6.6% per annum, compounding monthly. The loan will be repaid, making 12 monthly repayments of $172.50. Model this loan using a recurrence relation of the form, etc. Okay, so V0 is going to be the $2,000, the initial value of the loan. And then Vn plus 1, now we need to work out R, okay, so this is not even lowercase r because we're paying monthly, compounding monthly, so lowercase r is going to be 6.6 on 12, 6.6 on 12, so that is 0.55% per month, okay, so then to work out uppercase r, it is 1 plus 0.55 over 100, which is going to be 1.0055. You can check that. 1 plus 0.55 over 100, 1.0055. So that's our multiplying factor from month to month. We multiply by that. That's increasing by 5.55% per month, which is equivalent to 6.6% per annum. So we're doing that times Vn. And then we're also going to subtract our monthly repayment, which is $172.50. Now, in further maths, we'll always deal with loans where, and realistically, it's the more common thing, always deal with loans where the interest is added on first and then you subtract the payment. Okay, so it's always going to follow this model. Use the recurrence relation to determine the balance of the loan after 6 months. Okay, so let's set up our CAS. So we're starting with 2,000, we're multiplying by 1.0055, and then subtracting 172.5. So it's up to 1 month, 2 months, 3 months, 4 months, 5 months, 6 months. So after 6 months, the balance of the loan is $1,017. And remember, in financial maths, always rounding to the nearest cent, so 58 cents. What will the final repayment need to be to ensure that the loan is fully repaid after 12 months? Okay, so let's work out what V12 would be if we were to continue with this same pattern. So we're up to V6. 7, 8, 9, 10, 11, 12. Okay, so V12 would be $2.29. Okay, so what we would see is the value after the loan is $2.29. It's not negative. We haven't overpaid. We still actually owe $2.29 if we were to continue this situation. Now, what we don't want to do is we don't want to let that carry over to a 13th month, earn interest again, and then have to make a payment of about $3 again in another month, okay? We just want to pay it off at this point. So what we're going to do is we're going to need to increase our final payment, okay? So this means that our final payment, which will be the 12th payment, will need to be the original payment, which is $172.50, plus the extra $2.29, okay? So plus $172.50. Okay, so that means a payment of $174.79. So that means the next part of the question could be, how much is paid in total over the course of the loan. So if we wanted to work out, now this is beyond what the question's actually asking for, if we wanted to work out total payments, we've actually made 11 payments of $172.50, plus we've made a last payment of $174.79. And so we can work that out, 11 times 172.5 plus this payment. And so in total we've paid $2,072.29. That means the interest is going to be $2,072.29 minus the $2,000 that we borrowed, which means it is $72.29. We could work out an interest rate, how much the percentage of interest that we've paid by doing that as a percentage of 2,000, and find that we've actually only paid 3.61% interest over the course of those 12 months. Okay, so as I said, these are beyond the scope of what the question's asking you, but just the sorts of things that you might also be asked to do. So the work today is exercise 9A and also some questions from 9B.